Whenever we repeat a process that has very uncertain results, we call that a probability experiment. And one of the more famous probability experiments is, of course, tossing a coin. Let's say that for our probability experiment of tossing a coin, we focus on obtaining a head, specifically the probability of doing so. Students who come into this class already know that the probability of obtaining a head is 0.5. But there is a little bit more to it than that, just because if you think about it, let's say you tossed a coin 10 times. Would you necessarily expect to get heads 5 of those times? And obviously tails the other 5. Could it happen? Sure. But are we betting a lot of money that it's going to happen? Probably not. Why is that? Because generally chance behavior is highly unpredictable in the short term. We just don't know exactly what's going to happen with a small number of repetitions. All right, let's take a quick peek at a website that I found, which is called a virtual coin tosser. If you look down towards the left side of the page here, you're going to see that it gives you the option for the number of coins you're going to toss. We're going to stick with 1. And then it gives you the number of repetitions that you prefer to use. We're going to start with the 10 that we mentioned, right? Where the 50% means that we're sticking with a balanced coin. We toss it 10 times. If you look under frequency or experimental, you can see how many results. And if you look under results here too, you can see heads, 5 tails, 2 heads, blah, blah, blah. But the summary is down below here. So it looks like in our first toss of a coin 10 times, we got 4 heads and 6 tails. So that is not 50-50. We talked about that already. Maybe we try going to, let's go to 50. Okay, so toss. Okay, it looks like that time, interestingly enough, we got 25 on both heads and tails. If we do it again, you can see that it's way different. Only 19 heads and 31 tails. So extreme variation here going on. Why don't we increase that? Maybe go up to 500. Okay, we go up to 500. It looks like 52% heads, 48% tails. Maybe go to 5,000. We're getting close here. So 50.58%, 49.42. We do it again for the same one. It's 49.9 and 50.1. So think about it before. When we were doing it again for earlier, smaller repetitions, it vastly was different. Whereas now, if I keep on doing this and doing it again, these numbers are really close to 50-50. Now, we can even go more crazy. Let's go to 500,000. And you can see that these are getting closer and closer and closer to basically a 50-50 split. Why is that? Well, we have something called the law of large numbers. The law of large numbers basically states that if you increase the repetition of your probability experiment, so you do it many times, your probability that you obtain will get closer and closer to the true probability of running that experiment. This was evidenced by the fact that in the earlier repetitions, like 10 or 50, when I was hitting the toss button in the simulation on the website, the numbers were all over the place. They weren't close to 50-50 every single time. They were a lot of variation. Whereas when I got up into the 50,000, 500,000 range, all of a sudden the numbers were as close to 50-50 as possible there. Before we move past this, I wanted to just show some terminology. By showing you what I've shown you so far, we've actually sort of tripped on 2 different probability methods that we deal with. So we'll just say methods. So what are the two methods that we've already seen? Well, students right away know that the probability of obtaining a head when tossing a coin is 0.5. Well, where does that come from? It actually comes from what we call counting methods. Because when we toss a coin, we basically have two options. So out of those two options that we have, how many of them represents obtaining a head? Well, only one of them. Well, 1 out of 2 then therefore gives us the long range or long run probability of obtaining a head when tossing a coin. This is actually called the classical method of probability. Classical. On the other hand, when we went to this website and we started tossing coins and using experimental methods for figuring out what the probability would be in the long run by increasing the repetitions, this is called the empirical method. These also have different names in terms of other textbooks. For example, you might have noticed in my simulation there were two terms here in this table where it says outcome frequency. Well, the two terms are experimental and theoretical. That is actually what I'm more used to. So this is often called theoretical probability, and this is often called experimental. I don't know. I kind of prefer these only because this term empirical right here is confusing given you have learned about something called the empirical rule in bell-shaped distributions. But you're not really going to be asked per se for these methods on exam or anything like that, knowing what these terms are. But in the homework, they might mention these and tell you to do the problems in that way. I'm just sort of putting that out there so that you're not thrown off by what they're asking. Okay, while we're already in the world of terms, we might as well keep going with that and learn some terms that are going to help us along the way here. For example, there is a term called sample space. And basically what it is it represents all outcomes in a probability experiment. And why don't we use just to change things up, why don't we do a different probability experiment in order to sort of shed some light on this? So instead of tossing a coin, why don't we maybe roll a die? How about that? Roll a die. What I mean by roll a die is you guys know that when you play with dice, you have these 6-sided cubes, right? With the numbers on each side. Let's sort of stick to that as our probability experiment. So a sample space is usually defined by the letter S, and we list out all the outcomes in curly brackets. So if I wanted to know the sample space of rolling a die, then that would tell me all the outcomes I could get when I do so. Well, the outcomes are 1, 2, 3, 4, 5, or 6. So we would list them all out in curly brackets like set notation, and that would be defined as the capital letter S. And just to make sure you're following what I'm throwing out here, let's just look at our tossing the coin probability experiment. So if I wanted to do that sample space, then again, you would have to list all the outcomes you could get, and that the only outcomes you could get are heads and tails. Okay, we have yet another term that we will call an event. Event is basically any collection of outcomes from your sample space. We usually define events, again, with capital letters. In this textbook, they often use the letter E and then F. I've seen A and B a lot in other textbooks. I'm just going to be consistent here. Since it does say event, we'll just use E. So what we would have to do is we would have to define some event. So let's say, for example, that I define the event any even number rolled when you roll a die. So therefore, what are the outcomes of rolling an even number die? Well, when you look at our sample space, which is our collection of all outcomes, you can pick out the even values. They would be 2, 4, and 6. Therefore, there are 3 outcomes in this event. Again, we do it just like set notation with curly brackets. Okay, so we are going to find the probability of this event right here in 1 second. But first, let's define some rules of probability. First things first, if we want to find the probability of an event, we usually use the symbolism capital P for probability, parentheses, and then we put the letter that signifies the event. In this case would be probability of E. So this means probability of event E. Okay, anytime you have the probability of any event, there are 2 rules that must be followed. The first thing is the probability of said event must fall between 0 and 1 and potentially including 0 and 1. So you cannot get negative probabilities and you cannot get probabilities that are greater than 1. Second, the probability of the sample space is equal to 1. This is often a little bit difficult for students to wrap their heads around or try to understand, so I wrote out something here that makes it a little bit easier. Basically, the sum of the probabilities of all outcomes in the sample space is 1. Okay, so what does that mean exactly? Well, let's use our example up here. If we were to take the probability of tossing a 1 or rolling a 1, probability of rolling a 2, all the way up to 6, that means if you take all of those individual probabilities and add them together, the sum of those probabilities should be 1. Okay, so now that we know the rules of probability, let's actually find the probability of the event up here, this guy. Let's look at, first of all, the definition of probability. Remember, P of E is how you write it. You can see here that the probability of E is always going to be equal to the number of ways that E can occur over the number of possible outcomes. Another way to write this is the number of possible outcomes in the sample space, but further symbolized, they often, at least in this textbook, they write N of E over N of S. So this would represent number of ways you can run event E, number of ways in the sample space. So let's go up here and find that probability. So I usually start with the denominator first. That's usually the easier one because that's the original experiment's results. So look at the number of outcomes, this right here. Look at the number of outcomes in S right here. Well, it looks like there are 6 outcomes. So therefore, this number would be 6. Now, if we look at the numerator, this is the number of outcomes in the event E. So if you go here, you can see, remember this was the even rolled, getting an even rolled die. There were 3 outcomes in this result. So therefore, this would be 3 out of 6, which would give us 0.5 as our probability. And of course, you'll notice that our 0.5 here is clearly between 0 and 1 because it has to be. But generally, what I find with students is they already have this entire formula here in their heads. And when they do probability, they're like, okay, number of total outcomes on the bottom, number of ways it happens on the top. Basically, that's it. That's what it is. So it's not really about memorizing a formula because most students already know it already, but I'm just reiterating both the formula and the important rules that you must follow in the world of probability. And to be clear, this is a perfect example of classical probability. Whenever you use counting methods and calculate the probability from scratch without an experiment of any kind, then that would be an example of classical probability. All right, let's look at an example. It says, suppose that a survey asked 500 families with 2 children to disclose the gender of their children. Also, let's say that 120 of the families had 2 girls. We're going to let the event E be having 2 girls. It says A, estimate the probability of having 2 girls in a 2-child family using the empirical method. So if you recall here, I mentioned that the empirical method is often called the experimental method. So the probabilities that you get from this method are things that you are actually doing in a real world setting, like giving a survey or running an experiment, something like that. So you're getting data and you're actually coming up with a probability as a result. So therefore, in this problem, that should be pretty straightforward because they gave us some information. So first, remember, if I want to find the probability of the event E, I would write it like this. The event E is having 2 girls. Remember, according to the formula, which is right above us right here, that is the same as the number of outcomes in event E over the number of outcomes in the sample space. Now, I usually do the denominator first because that's everything. And when I say the number of possible outcomes in the sample space, in this scenario, it literally is the number of outcomes in the sample. And in this case, there are 500 families that were asked what the gender of their 2 children will be. The number of outcomes in the event, we also have that information because they said 120 families actually ended up responding that they have 2 girls. And if you do the quick math here, that's going to be a probability of 0.24 as our experimental or empirical method way of finding the probability. Okay, now it says compute the probability of having 2 girls in a 2-child family using the classical method. This is also the theoretical method, often called, assuming that boys and girls are equally likely. Okay, so what does that mean? That means we need to use counting methods in order to determine what this probability is going to be. So what does that mean? That means we have to create the sample space ourselves. So we start with S and curly bracket. So what would be one example of having 2 children in terms of gender? Well, that could be exactly what we're looking for, girl, girl. What could be another one? Well, it makes sense that it'll also be boy, boy. But we could also have mixed, so boy, girl, or girl, boy. There are no other options, which means the number of outcomes in our sample space, if we were to write this out again, NE over NS, is going to be 4. So if we're looking for our event E, well, what is our event E? It's the probability, it's the outcome of having 2 girls. So that's just this. So therefore, how many outcomes do we have in event E? Only 1, which means our probability is 0.25. For C, it says the probabilities that A and B are similar. How could we alter the setup of the original problem to ensure the probabilities are even closer in value? Okay, so it's good that they're close because remember the whole point was the empirical method eventually becomes the probability eventually becomes the same probability for the classical method. We did that when we were talking about flipping the coin, if you recall. Very few coins, we're not exactly sure what probability you're going to get for heads. But when it got towards 500,000 outcomes, then it was right on the money pretty much that it was half and half. So thinking along the same lines, for our empirical method, we only had 500 families. So how do you think this number here would end up being more accurate towards the classical method probability, which is here, by taking more families? So essentially, sample more families. All right, let's do a different example here. Suppose that we have a bowl filled with 3 red, 5 white, and 4 blue cubes. What is the probability of selecting a white cube? Okay, so let's let, as I did over here, let W be equal to, or the event W be equal to selecting a white cube. I purposely used a different variable just to make sure you have a different perspective on how these events could be named. So yes, we're trying to find the probability of W, which means that we need to find the number of outcomes in the event W out of the number of outcomes in our sample space. So the reason why I'm doing a couple different problems here is it just gives you an idea of how things look when it's a different example. So in this case, we have cubes, right? Cubes in a bowl, which means our sample is basically going to be all the cubes. So if we were to look this up and we're like, okay, well, we have 3, 5, and 4. So 3 plus 5 plus 4 is going to give us, looks like 12. So that means the number of outcomes, in this case, cubes, in our bowl is 12. And if we want to find the number of outcomes in our event W, that would be selecting a white cube. So how many white cubes are there? It looks like there are 5, which means, believe it or not, that's it. 5/12 is your probability, which, by the way, in a calculator would give you 0.417 approximately. Don't worry too much about decimal places for now. When we get a little bit farther in the unit, we'll talk more about it. Yet another example. It says, when flipping 3 coins, find the probability of getting the same result on all 3 flips. Already here, defined F as getting the same result on all 3 flips. So yes, our goal here will be to find the probability of F, which will be the number of outcomes in the event F over the number of outcomes in the sample space. Okay, this problem is a bit more challenging, and I would relate it a lot to this problem right here, because if you recall, we had to use counting methods and find the probability from scratch using a sample space that we created. That's going to be the same thing here. Whereas in this problem, we have the sample space literally drawn out for us. We don't really have that because do we know how many outcomes are there for flipping 3 coins? Maybe you do know that off the top of your head, but most usually don't. So we're going to have to figure that out. Okay, so one way to figure this out is to use what we call a tree diagram. Tree diagram is very helpful for figuring out a sample space. For example, if you're flipping 3 coins, you got to start with the first coin, right? So let's say on the first coin, you end up flipping, and of course the options that you can possibly have for flipping that coin are heads or tails. Okay, well, let's say you did flip a head on the first coin. What are the options on the second? Well, again, the second coin could be heads or tails. But what if you flip tails on the first? Well, that also would be heads or tails on the second. And hopefully you can see where this is going. Let's say you did heads and heads on your first 2. Then the option on the third is heads or tails. Same thing if you did heads then tails. You could have heads or tails on the and so forth. So here we go. For every single one of these outcomes, you could get heads or tails on the third result. So believe it or not, that has actually generated our sample space for us. So what do I mean by that? Well, if you look at the upper tree all the way through of this, one outcome that we could get by tossing 3 coins is all 3 heads. But if you, let's say, go a different way, we could get heads, heads, tails. The reality is every single one of these guys over here is the last coin in basically an option for a sample or an outcome. So we have heads, 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 tails. So that pretty much eliminates all scenarios with this branch right here. So now we go down to heads, tails, heads. And heads, heads, tails, tails. And that eliminates these guys right here. And then we got tails, heads, heads. And THT. And then that'll get rid of this guy here. And then finally, we'll get this guy and then this guy here. So we got tails, tails, heads, and tails, tails, tails. Looks like I made a pie there somehow. I don't know how that happened, but let's get that out of there. So tails, tails, heads. Once you have the sample space, you're pretty much good to go. It was very similar to this problem right here. Once we had that, we knew there were 4 outcomes. We just had to figure out how many were in the event E. So we're going to do the same thing here. So we know that there are, looks like 8 outcomes right here, which means there are 8 outcomes of flipping 3 coins. But we need to know the event F. Well, the event F, which is getting the same result on all 3 flips, that can only be 2 things, heads, 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 or tails, 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 which is exactly what they're looking for, which means 2 out of 8 is going to be our probability, or 1 out of 4, and if we get a decimal value for that, we get 0.25. So again, this is a little bit trickier because you have to develop your own sample space. Okay, there's one small concept we just have to make sure to cover before the end of the lesson. I'm going to use this example as sort of a lead-in. It says the color of plain M&M milk chocolate candies can be brown, yellow, red, blue, orange, or green. According to M&M Mars, their parent company, the probability of each is as follows to the right. Okay, so over here what you see is all 6 colors and the probability in which they should occur. Note, this entire thing right here is called a probability model. All probability models must fit the rules of probability, which you have seen up here. Okay, this guy here, so they must fit the rules, those basically. I'll highlight them. So all the individual probabilities must be between 0 and 1. And the probability of all the sum of all the probabilities in the sample space must also be equal to 1. So let's just check that out. So let's just say, for argument's sake, they asked, hey, like let's write this out. Verify this is a legitimate probability model. I already told you it was 1, so normally you would have to prove it yourself, but I did tell you. But for this, I'm just showing you how you would do that. Well, you would look at these, you would say, okay, all the probabilities are between 0 and 1. Looks pretty good there. So that's a check, right? Check. I'm running off the side of the page here. There we go. And sum of all probabilities should be equal to 1. Oh, you can break out your calculators if you want, but we have 7, 10, it looks like 20, carry the 2. Looks like it's going to be 2, 4, 6, 7, 8, 9, 10. Perfect. So it equals 1. Okay, so therefore, since these 2 qualify, then it is a legitimate probability model. One thing to note here is that a probability model is basically the same as a relative frequency distribution. So if you recall, the relative frequency distributions basically had all these proportions here. Well, proportions and probabilities are basically the same thing. So what we're looking at is just realizing that we're not doing anything different. For example, if you were given, instead of this scenario, you were given, let's say, the colors and the counts of them. So for example, if you did, I don't know, maybe an experiment with like 10,000 bags of M&Ms, that sounds amazing. eating them all, you would basically have counts there, right? And that would technically be a frequency distribution. So if I asked you to find the probability model, then all you would have to do is take all those counts out of the total, and that would give you, yes, a relative frequency distribution, but now it would also be a probability model. So just keep that in mind when you're doing the assignments. They'll probably ask you to do something like that.